Okay, let's talk more about radiation pressure. So, we're ahead of our homework, by the way. This is not in the homework, that'll be the next time, stuff like this. So remember the idea is we have this perfectly reflecting surface, it never met a photon that it couldn't reflect. And so here's radiation coming in from some solid angle cone size d omega. Law of reflection says that it bounces off the surface, so to speak, it reflects at the same angle of reflection with respect to the normal to the surface as the angle of incidence. And so if you think about it, every photon that arrives from this solid angle cone will be reflected into a solid angle cone of exactly the same size and exactly the same angle away from the normal. And so we're going to consider the momentum transfer by the photons that are reflecting off of that surface because their momentum is changing. They're coming in with downwards momentum, they're leaving with upwards momentum. So there is a change in their momentum. And so we can say that for a photon with momentum P equals E over C, because that's what the relation is between momentum and energy for photons, with momentum P equals E divided by C, the change in the Z component of momentum, because the component parallel to the surface doesn't change, but the Z component momentum does, the change in the Z component of the momentum going to be, we'll call that delta P sub Z. That'll be PZ final minus PZ initial. That'll be, well, the final Z momentum will be, E cosine theta over Z, because it's moving upwards in the plus Z direction, and we have to project along the Z direction here, right? So if the momentum is pointing as indicated, that's the hypotenuse, and so the projection along the Z axis is hypotenuse cosine theta. So that's going to be E cosine theta over C, E over C cosine theta, because the total momentum is E over C, project along the Z axis, you get E over C cosine theta. And for PZ initial, what's PZ initial? If PZ final is E cosine theta over C, what is PZ initial? Plus or minus. So the PZ initial is the incoming Z component of the photon's momentum. PZ final is the outgoing Z component of the photon's momentum. Is PZ initial plus or minus? It's negative because it's moving downwards and we're choosing plus Z to be upwards in our picture. So PZ initial is downwards and equal to what? Is it the same or different in magnitude than PZ final? It's the same, right? It's just going the other direction. Other than that, same energy, so therefore the photon just reflected, it's got the same energy, and so therefore that'll be minus E cos theta over C, and so minus is plus, and so the change in the momentum, the change in the Z momentum is twice the initial Z momentum, 2E cosine theta over C is delta PZ for each individual photon. What questions might you have? Comments? Observations? Note this would apply just as well if I bounced a basketball off the floor, right? The basketball transfers momentum to the floor, and assuming that bounces elastically off the floor so that its kinetic energy after reflection off the floor, so to speak, after bouncing is the same as it was going in, then the change in its vertical momentum is in magnitude twice the incoming momentum. It's equal to twice the outgoing momentum if we take plus to the upwards. We have lots and lots of photons reflecting from the surface. All their momenta are changing. So since the photon momenta are changing, gee, is momentum supposed to be conserved? Yes. Yes, yes. Please, everybody say yes, right? So if the photon momenta is changing, since momentum is conserved, whatever momentum is being transferred to the photons, equal and opposite momentum is being transferred to the surface. So light pushes, light exerts pressure, because upon reflection from the surface, those photons' momenta are changed. So the change in the momentum of whatever this is a surface of is equal and opposite to that. Yes?
Does it mean perfectly reflecting mean it doesn't absorb any momentum?
Yeah, we're saying here that it's perfectly reflecting. So if we were talking about a perfectly absorbing surface, well then we wouldn't have that minus piece. The perfectly absorbing surface would pick up the full momentum of the incoming photon. So in other words, not only would it acquire z momentum here, it would also acquire horizontal momentum as well in that case, because then you're also changing every component of the photon's momentum. It's going away. But for our perfectly reflecting surface, all that happens is it's pushing perpendicular to the surface. It really is acting like a pressure, in other words. What other questions might you have? Let's continue then. So, if, and it is, dE lambda, which is, as always, I lambda d lambda, I have to erase this right low enough so that you don't, I lambda, I sub lambda d lambda dt, dA cos theta d omega is, right, so all I've written here is the definition of specific intensity, but instead of having all those divisions under the dE lambda, I just moved them over to the side that has I lambda in it. So dE lambda equals all that stuff is the energy arriving in time dt from wavelength range, or in, I'd say, in wavelength range see if y'all have been understanding what I've been saying. What's the wavelength range I'd be talking about here? From what to what?
Lambda to d.
Yeah, lambda to lambda plus d lambda, a little narrow range of wavelengths. In wavelength range, lambda comma lambda plus d lambda, meaning in other words, in that range of wavelengths, from solid angle d omega, one indicated there, from solid angle d omega at angle theta to the normal. So in my notes I just summarized all that as, what did I say? From solid angle d omega, etc. But I figured I'd just write the whole crazy thing in there. Onto area dA. Onto area dA. And it is that because that's the definition of what I lambda is. That dE lambda is I lambda times all those things. Then, I'll wait until you all are done writing before I do the next thing. I just want to double check if that was recording. I didn't recharge the microphone, so it's just camera sound. So I'll do the thing. I'll fix it in post. I'll boost the sound level in post. I just believe that I can do that. is glorious. But anyway, okay, y'all caught up with the writing there? Then, how much momentum? All that, right? dp lambda, that'll be 2 dE lambda cos theta over c. In other words, I just replace E in this expression for each individual photon with dE lambda to represent the effects of all those photons coming in time dt, in blah, 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 equals, well then that's 2 over c I lambda d lambda dt dA. But it's going to be cosine squared theta, because it's already got a dA cosine theta there, so the dE lambda cosine theta is going to put another factor of cosine theta to that one. Cosine squared theta d omega where it's understood that we're talking about the component of momentum normal to the surface, right? This z component here. So even though I'm not saying dp lambda sub z or anything like that, it's understood here that that we're discussing the component of momentum normal to the surface. Now, pressure is what again? What are the units of pressure? Newtons per square meter, right? It's force per unit area. And let's see, force is the rate of the force that's applied to the surface will be the rate of transfer of to the surface. So F is MA is also what? dP dt, right? Force is rate of change of momentum for a particle. Or if I'm talking about my surface here, the force on it is the rate at which momentum is being transferred to it. So in other words, what we say next is now dP lambda dt divided by dA should be the pressure. dP lambda dt divided by dA is the momentum transferred per second, because we're dividing by dt there, per second per square meter to the photons. So minus that is the rate at which momentum is being transferred per second per square meter to the surface, because we've considered the change in the photon's momentum, but that's equal and opposite to the momentum that we're transferring to the surface every second. So minus dP lambda dt over dA is the momentum transferred per second per square meter to the surface. That's the radiation pressure. Momentum per second per square meter transferred to the surface, that's the force on it, that's the pressure. I should say, due to those photons impinging upon it, is the momentum transferred per second per square meter to the surface Now, when we talk about pressure, we don't consider it plus versus minus. We always consider it positive. So in other words, with pressure, it's just a single number. In other words, we don't talk about the pressure being minus on one side of the surface and plus on the other side. We just talk about the pressure, and it's understood that the force due to the pressure is pushing on the surface perpendicular to it. Okay? So in other words, I'm not going to care about that minus sign right there when I'm talking about the radiation pressure. If I want to know the force, I have to know, okay, if the photons are coming from above it, I would know it's pushing down on it. But if the photons were coming up from below, what would they be doing to the surface? They'd be pushing up on it, right? So we don't care about that minus sign. So what we conclude here is that in magnitude, dp lambda dt over dA there equals the radiation pressure on the surface. Per unit wavelength interval here, right? In other words, the radiation pressure due to photons in that wavelength range. Photons in all these intervals, right? In other words, within d lambda and from d omega. This is only for photons in wavelength range d lambda and coming in from solid angle d omega. So what would we do to get the pressure in wavelength range d lambda overall? Here we've only considered photons coming in from d omega, so what do I have to do to get the total pressure on the surface from all the photons impinging upon it? What's that? Yeah, I gotta do an integral, right? And I'm gonna do an integral over the outward hemisphere, over all incoming directions, right? So here I wouldn't go below the surface. In the middle, I'm going to do that. I'm going to remove the reflecting surface. Because just like in this room, there's still pressure in the air, even though I don't have a surface right here that the air molecules are bouncing off of. I still talk about the air pressure due to molecules transferring momentum through the surface as they fly through it, as opposed to here on the walls, the air molecules are bouncing off the walls, more like that situation. We still talk about the air pressure in the room, even if they're not bouncing off of some surface. And so we're going to do that in a minute with our photons. With our reflecting surface here, if I want to know the total pressure on it in this little wavelength interval, I have to integrate over solid angle. Does that make sense? What questions do you have? Okay. So, can I erase this stuff? That's not supposed to be lambda, it's supposed to be d lambda. D lambda and d omega. So to find the total radiation pressure, the radiation pressure as it were, total radiation pressure per unit wavelength interval which we'll call P sub rad comma lambda, and then to get the total radiation pressure, we would also have to integrate over wavelength as well. We'd integrate over our wavelengths. We integrate over solid angle in the incident hemisphere. So in other words, P rad lambda will be integrating this beast right here over d omega in the incident hemisphere. So it will be 2 over c is a constant, so we just take that out of the integral. I lambda cosine squared theta d omega, because we've already divided by dt and dA, right? We're taking dp over dA dt and integrating that. So this piece right here is our dp lambda over dt dA. So those pieces have gone away. And then we still got the d lambda, the cosine squared, and the d omega. But I've also taken out the d lambda because I want it to be just p rad lambda by itself. If I wanted, I could say that the total pressure in that wavelength range would be p rad lambda d lambda, and I could throw a d lambda on both sides. Or I could just leave the d lambda out and say I'm just finding the thing that I multiplied by d lambda in order to find the pressure due to photons in wavelength range d lambda. So you could optionally put a d lambda on both sides if you want to emphasize, well, here's the radiation pressure from lambda to lambda plus d lambda. If I don't put it there, I say I'm finding the thing that you multiply by d lambda to find the pressure due to photons in range lambda to lambda plus d lambda. Did what I just said make sense, or are you like, what are you talking about? Yeah, so P rad lambda d lambda would be the radiation pressure due to photons in the range from lambda to lambda plus d lambda. Photons with wavelengths in the range lambda to lambda plus d lambda. So I could say then, okay, well then P rad lambda d lambda is all this stuff, and I still multiply by d lambda over there too. Or I can say, yeah, fine, so I'd have a d lambda here, I'd have a d lambda here. Or I can say, well, what I'm finding is the thing that later I will multiply by d lambda in order to figure out how much radiation pressure there is from that range of photon wavelengths. Does that make sense? Happiness, joy, lack of happiness. And what is it that you cannot read, Kathleen? P rad comma lambda d lambda equals radiation pressure due to photons with wavelengths in the range lambda to lambda plus d lambda.
Thank you.
Yes.
My glasses are not the right.
Ah, okay. You should fix that.
Yeah,
Because it turns out you can see the board better and everything. Yeah.
insurance won't cover.
What? Oh, man. Huh. Okay.
Now you need to read it out for me.
Yes, that's right. So P rad lambda equals,
Bigger.
wow, I'm gonna be running around a lot. Yeah. V next.
One more for every.
Yeah, that's right. Yeah, one word per word. That's right. Yes. Okay. So this is the integral I want to carry out here. And it's got to be over the incident hemisphere. So that'll be 2 over c. And now let's do it in spherical coordinates first. So incident hemisphere is going to be theta equals what to what, phi equals what to what. I lambda cosine squared theta d omega. So if we're only looking at the incident hemisphere, what range of phi values is that? Yeah, all the way around, right? Every azimuthal direction, right? Yes. It's about right. We're doing spherical coordinates, right? Yes. Okay. So phi goes from 0 to 2 pi, and then for theta,
5.
0 to, but it's only the incident hemisphere, so only down to here, right? 0 to pi over 2, 0 to pi over 2. So I'm doing phi and theta. 0 to pi over 2. So anything depend on phi in I lambda cosine squared theta? Maybe. But if I lambda is azimuthally symmetric, in other words, if I lambda does not depend on phi, then I can do the phi integral separately. So I'll say this over here. I actually used up some oxygen. All right. I'm breathless. Oh, this is so exciting. Oh. If I lambda does not depend on phi, we can do the phi integral first. I think I forgot to point that out in my notes, but that's okay. I'm doing it here. Right. So when I do that, the phi integral just gives 2 pi. So we get 4 pi over c. And get that our p rad lambda is 4 pi over c times the integral from theta equals 0 to pi over 2 of I lambda cosine squared theta times sine theta d theta. Oh yeah, I should have written this d omega as over here. I should have written that as, remember, that's sine theta d phi. I should have put that in for d omega, right? So now we've got cosine squared theta, sine theta d theta, sine theta d theta. Gosh, what substitution should we make here? Let's do this by an integration by substitution. What's our standard substitution? Mu. Yeah, mu is cosine theta. That's right. Think like a cow. Cosine theta, right? So we say again, put mu equals cos theta, right? And then of course it's the usual, right? And d mu is minus sine theta d theta, and I'll just write it down. We've done it before, but let's do it again. Mu of 0 is equal to cosine of 0 is 1, mu of the upper limit, pi over 2, is equal to, what's mu of pi over 2? 0, because cosine of pi over 2 is 0, right? And so when you do all that, this is going to turn into 4 pi over c, and then the minus sign will flip the limits to get rid of it, and it'll be the integral from 0 to 1 instead of from 1 to 0. It would be minus the integral from 1 to 0. Ew, who wants that? So we flip it and make it the integral from 0 to 1 of I lambda, and then this is going to give us, it's really minus mu squared du, but again, when we flip the limits, it turns into just mu squared d mu. Or in other words, as advertised, the radiation pressure is proportional to the second moment of the radiation field, meaning we multiply by mu squared and then integrate. We multiply by cosine squared theta and then integrate. I did say in my notes afterwards, where the last step assumes I lambda is independent of phi. Okay. So, this is what we were after, you may recall from last time. Yes?
Are we totally going to extend that I lambda is going to be independent of the no pi or phi?
So, in general, it is not, but it often can be taken to be so for a star, for the radiation field inside a star, because a star is spherical, right? And if you are at the surface of that star, right, so imagine this, the floor is the surface of the star, even though stars don't have perfectly well-defined surfaces, they're balls of gas, blah, 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 shut up. This is the surface of the star. If the star were completely featureless, it's just a cue ball, is there any variation in the specific intensity? So here's the normal to the surface. Okay, here I am sweeping out angle phi. Should the radiation depend on direction perpendicular to the surface? That's why we are just often taking I to be azimuthally symmetric, because it often would be. There's no reason to think that the star's brightness varies in different directions. If you're the same angle away from the perpendicular surface, often there's no reason to think the star would look different brightnesses at different azimuthal angles around that.
What would make us like change to I lambda to be independent by what?
So, for example, why you might be at the edge of a star spot. Oh, here's a star spot right here, okay? So if I point in this direction, somebody looking back in that direction sees normal brightness photosphere. But somebody looking back along this direction sees star spot. So in that case, it would not be azimuthally symmetric. So yes, in reality, you can certainly have a non-azimuthally symmetric radiation field, particularly near the star's surface. But in the star's interior, because we're going to be interested in what's the radiation field inside the star. In the interior, typically, there's no particular reason to think that the radiation would be different depending on azimuth. It should just be symmetric around the line towards the center of the star. And so, to keep things simple, we're sticking with azimuthal symmetry being assumed. Yep. Great question. What other questions? Anybody else have a great question for me? Because I do love my good quality questions. So I'll just, since it was all the way since Monday, since we said this, I'm going to add here. So indeed, P rad lambda is proportional to the second moment of I lambda. In other words, what you get by multiplying by 2 powers of cosine theta and integrating. course, we talked about the net flux. That was proportional to that was depending on the first moment, where we just multiplied by cosine theta, as opposed to cosine squared theta. Okay. So, now I'm going to make a subtle argument here. And so, if you're not buying what I'm selling, let me know. Okay, so imagine, here we are, we're bathed in photons everywhere. I have this perfectly reflecting mirror, and it's having pressure put on it from above by the incoming photons. If the radiation field is symmetric, okay, there's photons coming up from the bottom too. Compare the force, if it's isotropic, compare the force of the photons impinging upon it from the top to the force from the photons impinging upon it from the bottom. Are those two forces equal or different from one another? They're equal, and are they in the same direction or opposite directions? Yep. So they're equal and opposite, so what's the net force due to the photons? 0, right? And so there would be no net force on it, even though there's a pressure everywhere. Push down just as hard as push up, as long as it's symmetric. If the radiation field is asymmetric, if it's not isotropic, this is what happens in a star where there's more radiation flowing out than flowing in. Suppose there was higher specific intensity in upwards directions than in downwards directions. Would there now be a force on my mirror? There would. What direction would the force be? Up, right? It would be up. So in the star, the radiation field, because it's not isotropic, because it's brighter going out than going in, there is a net outward radiation pressure as a result of that. And in this room, right, photon pressure, the concepts are quite similar to gas pressure. Okay, with gas pressure, instead of molecules, instead of photons, quote unquote, bouncing off things, it's molecules, right? In the room, as long as the pressure is the same everywhere, then there's no net force on any surface because the pressure pushing up is equal to the pressure force pushing down. On the other hand, if the pressure were increasing downwards and I had some slab of some finite thickness, so that there was a pressure difference between the top of it and the bottom of it, then there would be a net upwards force on it. And we'll get to that inside stars when we talk about hydrostatic equilibrium. We'll find that pressure does increase towards the star's center. It has to, because the pressure force on any little slab from the bottom pushing up needs to be higher than the pressure force pushing down from above, because the slab has weight, and that net upward pressure force has to balance the gravitational force on the slab. Back to our story with our photons here. So consider the following. Now, here we are, we've got this perfectly reflecting mirror, and I remove it. What's that do to our calculation of the pressure? Well, what that does is what we can say is now, okay, this photon streaming along this direction, what's it do? It doesn't do that anymore. What's it do? What's it do at this point? If I remove the mirror, it just keeps on going, right? Keeps on going. But consider this photon right here that reflected off of the mirror. If the radiation field is isotropic, then surely, essentially, well, there's some other photon that was coming from below that is going to sort of replace that photon that got reflected, right? In other words, here's a photon, here's a photon, here's a photon. If the mirror's there, they do this. They just reflect off in opposite directions. But if the mirror's not there, they just crisscross, and the effect is the same. The effect is essentially the same. Any photon that gets reflected, well, if you take away the mirror, it's replaced by another photon that just happened to pass through the surface at the same time that the other one was that got reflected. So in other words, and I'll write this out, in other words, if we take away the mirror, then we just integrate over all directions to get the radiation pressure, because if we think in terms of momentum transfer, photons flowing from above are transferring downward momentum. Downward momentum is flowing into the surface from above. And upward momentum is flowing into the surface from below. So there's downward momentum flowing in and upward momentum flowing out. But if you kind of keep track of the algebra, upward momentum flowing out is the same momentum transfer as downward momentum flowing in. And so in the end, the pressure that we want to get, we can do exactly the same thing in terms of the momentum transfer. The momentum transfer through the surface is the same whether or not you've got the mirror there. It doesn't matter whether you're talking about photons bouncing, doink, doink, or crisscrossing. There's still momentum being transferred through that surface. If we take downwards to be the, well, which way do I want it? If I take upwards to be the positive direction, then from above, is it positive or negative momentum that is flowing through that surface? If I take up to be the positive direction, and I get rid of the mirror, so it's just a hypothetical surface in space, is there positive or negative momentum flowing into that surface due to the photons streaming through it? If up is positive, here's all these photons flowing down through it. Is upward or is positive or negative momentum flowing through that surface? Is it upward or downward momentum that's flowing through the surface due to those photons coming from above? It's downward, and if I take up to be positive, is that positive momentum or negative momentum? It's negative momentum, right? So there's negative momentum flowing in, right? And meanwhile, from below there are photons flowing through the surface. Are they transferring negative or positive momentum through the surface? Positive momentum, right? So there's negative momentum flowing in and positive momentum flowing out. But negative momentum flowing in terms of the force, is the same as positive momentum flowing out. Think of it like charge. Think of it like electric charge. If I have negative charge flowing into a surface, what does that do by itself to the net charge inside that surface? Makes it more negative, right? If there's negative charges flowing into some surface, it's becoming more negative. If there's positive charges flowing out, what's happening to the charge inside the surface? Is it becoming more positive or more negative? Yeah, positive charge is flowing out. It's making it more negative, right? Negative charge flowing in and positive charge flowing out, both are talking, we're both talking about the inside of the surface. It's getting more negative, right? Now replace charge with momentum. Negative momentum flowing in and positive momentum flowing out would both reduce the amount of positive momentum within that surface. So they're both equivalent to one another. And you might think, well, what happened to momentum conservation? What happens is, let me talk about the air in the room, since that's maybe slightly more intuitive than photons. Okay, if I draw a box inside the room, there's a box. Actually, I'm going to go get one. It makes it more visual. I think I've got a box in here that I can use, a nice transparent box. I love the transparent box. Where's my fish tank? Where's a fish tank when you want it, huh? Let's see. Okay, not a fish tank, but whatever. Okay, pretend this is a fish tank, and also pretend it's just an imaginary surface hovering in the air. It's not on the table. It's just this imaginary surface hovering in the air. Okay? And we're going to take Up is positive. There's air, and this is an imaginary surface, right? It's not a real surface, it's imaginary. So through the top here, there are air molecules streaming downwards through that surface. If we take up as positive, are they transferring negative momentum or positive momentum through that surface? Negative momentum. Meanwhile, there's air molecules streaming upwards through the surface. So are they transferring negative momentum or positive momentum out of the surface? Positive. So through this surface, on the whole, there is negative momentum transferred through it, if we take out positive. So if that's all that was happening, the total momentum of the air molecules inside this surface would be diminishing with time. Not that the individual molecules are doing that, but in other words, if you added up the momentum, all the molecules in the surface, if all that was happening is up-flying particles were going out and down-flying particles were going in, the amount of positive momentum inside that surface would keep decreasing, because initially there was plenty of molecules moving upwards with positive momentum, but they're gone, and now there's a bunch of molecules in there flowing downwards with negative momentum, and they're there, so you have it switch from being plenty of positive momentum to, oh, now it's just all this negative momentum. So from this surface, the momentum transfer would be reducing the amount of positive momentum inside, increasing the amount of negative momentum. Oh, wait, you mean momentum's not conserved? The momentum inside the box is just like disappearing, or at least it's being transferred outside? I thought that in the room here, surely, what's the net momentum of the molecules inside this box overall? It's zero, right? Because they're going every which way, but the center of mass is just sitting there, so there's no net momentum in here. Resolve the dilemma. We just said that because of this surface, there is a net flow of positive momentum out of the surface, because there's negative momentum flowing in and positive momentum flowing out. Why this surface is causing the momentum inside this box to become more and more negative. So how is it staying zero? How is it staying zero? How is it staying zero? Is this the only surface? No. Find me another surface which might be having the opposite effect. Right there, right? That surface down there, the molecules that are flowing into it from the room, are they transferring positive momentum or negative momentum? Positive momentum. How about the ones that are flowing out of it through that surface from inside the box? Negative momentum. So due to that surface, is there a net positive momentum flow into it or a negative momentum flow into it? Positive. Compare the rate at which negative momentum is flowing in through here to positive momentum flowing in through here. Equal. They're equal. So what happens to the net momentum inside of this thing? Zero. It's not changing at all. So is there any force on it? No, because the momentum isn't changing. The momentum's not changing. And so, in other words, we can say that, yeah, there's a pressure here, there's a pressure here, and if we divide inside and outside according to this particular volume right here, then the pressure up here is associated with negative momentum transfer, and the pressure down here is associated with positive momentum transfer. But if the pressure is uniform, if there's no net momentum transfer, there's just as much momentum flowing into it from some surfaces. There's just as much positive momentum flowing into it from some surfaces as out of it from other surfaces. It's only if there's a pressure gradient, if pressure is different at different locations, that there's a net momentum transfer. If the pressure were higher down here than up here, and it is a little bit because of the fact that pressure increases towards the floor because of the need to support gravity and so forth, then the pressure forces would be producing a net upward transfer of momentum. And in fact, you would find that the thing's going to start moving upwards, that there's going to be a net momentum of the air molecules inside that box, and so on and so forth. And all that's to say, we can do the same thing with the photons. If I want the pressure on this, in other words, I could talk about okay, figure out how much Z momentum is transferred for all the things that are bouncing off this and integrate over the outward hemisphere. We do the same sort of thing. Or I can just say, okay, negative momentum flowing in, positive momentum flowing out are doing the same thing, so I can just integrate over the whole sphere instead of the hemisphere and take account of the fact that on the top side it's negative momentum flowing in, and on the bottom side it's positive momentum flowing out, which are both equivalent to negative momentum flowing out, or positive momentum flowing out, or equivalently negative momentum flowing in. Okay, that's my big long-winded explanation that sets us up for the break where we extend the integral over the whole sphere and then it's glorious, and then we proceed from there. Yeah! Yeah! Woo! Yes! I'm under so much pressure to get this right. Yeah, the fact that light exerts pressure is the principle behind solar sail. Solar sail, where you would have a spacecraft and you spread a big, very highly reflective sail
Hey, I don't know.
of sunlight and accelerate the spacecraft. What's that? You did a project about? Oh yeah. See, there you go. Oh yeah.
Whatever you want, you just say.
Yeah. And they said, yes!
Yeah.
Good!
I don't.
Oh yeah. Alright, let's do this. So, let's remove the perfectly reflecting surface and replace it with a mathematical surface. So this will be the short summary of all that stuff that we were just talking about. If we remove the perfectly reflecting surface, and replace it with a mathematical surface, in other words, just, it's a surface. There's nothing there, but it's a surface. And replace it with a mathematical surface. And as we were arguing, the incident photons continue past dA, representing a flow of negative Z momentum into it. Incident photons continue past dA, move right on through, representing a flow of negative Z momentum into it. Negative Z momentum into it. Well, photons streaming through from the other side take over the role of the reflected photons, right? So, you know what I'm talking about again. With the surface there, we get two photons kind of like doink, doink. But if you take the surface away, you get the equivalent. They just cross paths. These are photons that have the same energy that are coming in, right? So that they're equivalent to one another in terms of their effects. While photons streaming through from the other side take over the role of the reflected photons. Photons streaming through from the other side take over the role of the reflected photons. representing a flow of positive z momentum out of dA. Positive z momentum out of dA. Which has the same effect as a negative flow into the surface for the reasons that we were arguing before. Both had the same effect, that in and of itself, it would reduce the amount of positive momentum inside what was ever behind that surface. But again, if you've got a radiation field everywhere, well, that surface would be part of a box, if you like, and on the other side, there'd be there'd be positive momentum flowing in, making up for the negative, making up for the positive momentum flowing out equivalently through the top surface, if you will. So again, there's no momentum conservation being violated here. It's just that if you have a closed container, the net result over all parts of the surface would be no net momentum transfer, even though positive momentum is flowing into the volume in some parts of the surface and out of the volume in other parts. On the whole, that would cancel for an isotropic radiation field. And so the net result of this is we can remove the leading factor of 2 and extend the integration to all solid angles. I'm removing the leading factor of 2 because it came from saying that this photon, quote unquote, bounces and its change of momentum was twice the incoming momentum in magnitude. Well, no, now we're just taking all the photons, and these come in with a plus, and these come in, these come in with a minus, and these come in with a plus, and when you add them together, it's exactly the same thing as we were doing before. So, thus we can remove the leading factor of 2 and extend the integration to all solid angles. We just look at what each individual photon is doing as it crosses the surface. We don't need to talk about incoming versus outgoing for individual photons. We just look at what each one does as it crosses the surface. We can remove the leading factor of 2 and extend the integration over all solid angles. And so we can say that P rad lambda is just, instead of 2 over C, 1 over C, and then we integrate over the whole sphere, over solid angle, I lambda cosine squared theta d omega, and then y, that'll be now 2 pi over c instead of 4 pi over c, because now our phi integral produces a 2 pi, and it's not getting multiplied by another 2 this time. 4 pi over c, and instead of integrating from 0 to 1 on mu, it'll be from minus 1 to 1, because theta is going all the way to pi, instead of just pi over 2, minus 1 to 1 of I lambda mu squared d mu. And if our field is isotropic, if the radiation is the same in all directions, why, what could we do with that I lambda if it's the same in all directions? Comes out of the integral, right? So then this will just be 2 pi I lambda over c, And now I integrate from -1 to 1 of mu squared d mu, okay, 2 pi I lambda over c. What's the antiderivative of mu squared? Yeah, mu cubed over 3, so we get mu cubed over 3, put in 1, subtract what I get when I put in -1, but let's see, 1 cubed is, and -1 cubed is -1, so when I do 1/3 minus -1/3, that's 2/3, right? So this is 2 pi I lambda over c times 2/3. So in other words, I get 4 pi I lambda over 3c. So p rad lambda is, for an isotropic field, such as blackbody radiation, if the field is isotropic, the radiation pressure is 4 pi over 3c times I lambda. In fact, I think I'll do it that way. Of course, it's the same. But in other words, I want to say 4 pi over 3c I lambda to say, well, there's the factor that multiplies by I lambda to give you p rad, multiplies I lambda to give you p rad. So 4 pi over 3c I lambda for an isotropic field of radiation. What questions do you have? So we found the radiation pressure for an isotropic field. And again, well, not again, but I'll mention, pressure is a scalar, it's just a number. When you have a pressure force, it's going to be pointing, it's going to be perpendicular to whatever surface that you hold up to feel that pressure, and it's pushing on the surface, right? So the radiation to the right of this surface is pushing it to the left. The radiation to the left of the surface, from my perspective, pushing it to the right. Be flipped around for you folks. But anyway, pressure is a scalar. To turn it into a force, you need a surface. And the pressure force as a vector is the pressure times the area times the unit normal in the outward direction of the surface. The unit normal gives the direction of the pressure force. The pressure by itself is a scalar, and unit normal multiplied by the pressure times the area of the surface is the force that the pressure will exert due to material stacking into the surface. But again, there's also a force on the other side of the surface too. Let's keep that in mind. Okay, what questions do you have? Could this be any more glorious? No, it could not. It certainly could not. For thermal radiation, I consider talking about pressure to be kind of relaxing because I enjoy it. So it's kind of an irony there, right? I feel relaxed when I talk about pressure. In fact, I even feel relaxed in the physics sense. I feel relaxed talking about stress too, right? Like the stress tensor. So relaxing to talk about stress when it comes to physics. Maybe not other things. Normally I find stress quite stressful. But when it's physics stress, it's kind of relaxing and enjoyable. I just thought I'd point that out. So for thermal radiation, well, we say that I lambda is, of course, what's it be? If it's thermal radiation, if it's black body radiation, then I lambda is, what's it be in that case? B lambda, yes, come on, please. Work with me here. What's it be? I'm just trying to, right? It's, oh, man. I lambda is B lambda, which we have an expression for, right? 2 pi h, whatever all that stuff is, right? So we could write it out. What is it? 2 pi hc squared over lambda to the 5th over parentheses e to the hc over lambda kt minus 1, whatever it is, the Planck function. I lambda is B lambda. So therefore, if I want the radiation pressure P rad lambda, well, that's just 4 pi over 3c B lambda. And again, we have an expression for B lambda. We know what B lambda is as a function of temperature. So if we want, we can actually write it out. We know what P rad lambda is as a function of wavelength and temperature. To get the total pressure, total radiation pressure, two, 4, 6, 8. Now it's time to integrate. Yes, we got to integrate over wavelength, right? To get the total radiation pressure, we integrate over wavelength. Integrate over all lambda, and so that'll say that P rad, drop the lambda subscript, is just the total radiation pressure for our black body radiation, is 4 pi over 3c, integral from, what's the limits of my integration? If I integrate over all wavelengths, we're integrating from a wavelength of what to what? Yeah, 0 to infinity. The wavelength in principle can be anything. 0 to infinity, b lambda d lambda, right? In general, it would be I lambda d lambda, but we'd have to know what I lambda was to actually do the integral, and maybe it would be too hard. But we can do this integral for b lambda. We've done it before. We know that the integral of b lambda over all wavelengths is what? What's the integral of b lambda over all wavelengths? What's the, so f is the integral of f lambda over all wavelengths. And if it's for black body radiation, right, if we put in black body, well, I'll say in general it'll be f lambda. If it's thermal radiation, ideal black body radiation, oh, please tell me you know what f is for black body radiation integrated over all wavelengths. I mean, come on, there's like maybe some famous people that have their names attached to the equation that comes out like, what would that be? Yes?
F equals sigma t to the fourth.
Bingo, sigma t to the fourth, right? Stefan Boltzmann, right? Stefan and Boltzmann, right? You got to respect your Stefan and Boltzmann there, right? And realize this. Sigma t to the fourth. We know f is sigma t to the fourth. That's the integral of f lambda over all wavelengths for black body radiation. And then f lambda for isotropic radiation, which includes black body radiation. F lambda is what times? Pi, right? F lambda is pi b lambda. So in other words, the integral of b lambda over all wavelengths is 1 over pi of the integral of f lambda over all wavelengths. So this is 4 pi over 3c times sigma t to the fourth over pi. B lambda integrates to sigma t to the fourth over pi. F lambda integrates to just plain sigma t to the fourth. Let's see. And while you're pondering that, I'm going to go get another piece of chalk. It's your perfect opportunity to catch up because my chalk got all stumpy. see, can I simplify this? Yes, the pi's cancel. So we get a result of 4 sigma over 3c t to the 4th power. But wait a minute. Does anybody remember what we called that combination before? Because we had found before that u was equal to 4 sigma over c times t to the 4th power. And we decided, who wants to write 4 sigma over c all the time? So let's just call it a single constant. It would be a what kind of constant? It's a. It's just a t to the 4th. We just said that by definition that's a t to the 4th power is the radiation density, energy density, right? We found last time the energy density, I think it was last time, the energy density for thermal radiation is a t to the 4th, and we just discovered that the pressure is a t to the 4th over 3. We get the same thing, only it's over 3. So question, first of all, is that making sense? In other words, pressure and energy density, we're claiming they have the same units. Is that right? What's the units for pressure? Right, so pressure, unit-wise, pressure units are newtons per square meter. Energy density units what's energy density units? What's energy in SI? Joules, right? How precious. And what's volume? Because it's a density.
Joules per meter squared.
Yeah, so it's volume.
Cubes.
Cube, yeah. Right. Joules per cubic meter. Are these the same as one another? Well, what's a joule in terms of newtons and meters? It's a Newton meter, right? So this is Newton meters per cubic meter. Oh, it's also newtons per meter squared. Now, we're not going to call it newtons per meter squared because physically it's energy per cubic meter. But in other words, in terms of units, yes, pressure and energy density have the same units. That doesn't mean they're the same thing. They're very different things physically, but they have the same units. And so it's not surprising that P rad and U are both have the same units, right? They both have a t to the 4th, which has units. You can write it as newtons per square meter if you're thinking of it as in terms of the radiation pressure, or you can write it as joules per cubic meter if you're thinking of it as the energy density. And in the end, in other words, what we have found is that P rad is 1/3, and let's just call it U rad to clarify that this is the energy density in the radiation. So for radiation, the pressure is 1/3 of the energy density. Yes?
Should there be a 3 in the denominator of each to the 4?
Of this one? No, because the energy density doesn't have it. So U is the energy density. It's the energy per cubic meter in the radiation field. That's a separate derivation that leads to U is AT to the 4th power. Whereas the pressure derivation has AT to the 4th power over 3. In other words, U was 4 sigma over CT to the 4th, and we call A 4 sigma over C. And here, it's 4 sigma over 3C, so it's A over 3. So they're different things physically. They mean different things. One is how much energy is in every cubic meter of the radiation field. The other is how much pressure is exerted on a surface that you hold in the field. But they have the same units, and it ultimately, right, in other words, they're equivalent units, and the pressure is 1/3 of the energy density. That's a very fundamental result, that for radiation, the pressure is 1/3 of the energy density. let's compare this to an ideal gas. Compared to an ideal gas. So for an ideal gas, do you remember what's the ideal gas law? Yeah, Pivnerd, right, and all that, right? But in this class, we usually want to write it in a different way, which is it's the number density of the particles times the Boltzmann constant times the temperature. This is another version of the ideal gas law. It's entirely equivalent because if you do Pivnerd, now I have to try to do this right. Pivnerd says, right, PV is nRT, right? Or this is the number of moles, right? And this is the so-called gas constant. Well, just divide through by the volume. P is N over V RT, right? So it's the number of moles per unit volume times the gas constant times the temperature. But if you take the number of moles per unit volume and divide that by, if you take the number of moles and you multiply it by Avogadro's number, right, then that's the number of particles in the box divided by the volume. That's the number density. This is the number of particles per cubic meter. So it's Na over V RT. So in other words, this is N over V is the number density, number of particles per cubic meter, and Avogadro's number times, and I'm hoping I'm getting this right, I'm just doing it here, right? I think this is right. So if you're watching this later and I'm wrong, figure it out, okay? Just figure it out. So in other words, Boltzmann constant, if I did this right, is Avogadro's number times the gas constant. So entirely equivalent to one another. Okay, so, all right, but I did it basically. If I messed up, it's some little thing, okay? Leave me alone. So, yeah, it'll be right. It'll be like, yeah, but still, there's so much pressure up here. Do you understand how much pressure it is up here? Okay, let's see. It's not that much pressure. Oh, I'm talking about pressure. See what I did there? Yeah, so we want P is NKT. That's how we do it, okay? That's usually more useful to us. Equipartition theorem, which we've given a passing mention to, and if you take thermal physics, you definitely see this. The equipartition theorem says, if I have a monatomic ideal gas, then the energy density of the gas is 3/2 NKT, because each particle gets 3/2 kT of average thermal energy, and in an ideal gas, the particles don't have any potential energy of interaction. That's what makes it an ideal gas, is they don't interact with one another, other than maybe smacking off one another like hard spheres, so there's no potential energy there. So 3/2 kT per particle, right? 3/2 kT average thermal Ke per particle divided by the number of particles, turns that into number of particles per unit volume times 3/2 kT would be the total thermal kinetic energy per cubic meter. And so, therefore, for an ideal gas, how are the pressure and energy density related? How are the pressure and energy density, because look, they both have NKT, right? So P gas is what times U gas for our ideal gas here? No, well, they both have N, so we've got NKT, NKT. So U gas is 3/2 of what P gas is, or in other words, P gas is 2/3 of what U gas is, right? So for an ideal gas, the pressure is 2/3 of the energy density. But for a photon gas, if you will, thermal rate, this is in thermal equilibrium, right? An ideal gas in thermal equilibrium, the pressure is 2/3 of the energy density. For our photon gas in thermal equilibrium, because black body radiation is thermal equilibrium, it's 1/3 of the energy density, right? So there's a fundamental difference there, 1/3 versus 2/3. I'm going to have you guess. Let's see. If I make my ideal gas really hot, I start, the classical physics breaks down. Why? If I make my gas really hot, why would classical thermal physics start to break down for a very hot gas?
Pressure tend to infinity.
That's not in and itself a problem, because that would be true classically as well. But let's see, the temperature is related to the average kinetic energy per particle, right? So as I keep heating the gas, the particles go faster and faster. Is there maybe any kind of speed limit to all that? Speed of light, right? So if you heat the gas enough, the particles become relativistic. Their speeds become comparable to the speed of light. So if you have an ultra-relativistic gas of particles, that would mean the particles are essentially all moving essentially the speed of light. Not literally, because any particle with mass can't move the speed of light. But if I have an ultra-relativistic ideal gas, that's a good word, is it? Ultra-relativistic.
Did you just come up with it?
No, that's a thing. Good people will say that. Ultra-relativistic. Ultra-relativistic. I mean, it makes me want to do like, what is it, supercalifragilistic, ultra-relativistic ideal gas is atrocious, or something like that.
Of course it is.
Yeah, right. It's an ultra-relativistic gas. The speeds are so atrocious, or something like that. But if you figure out the answer to my next question, I'll say that you're precocious. Damn, that worked. Ultra-relativistic ideal gas. What do you think the pressure is related to the energy density for an ultra-relativistic ideal gas? Where the particles are essentially all moving so close to the speed of light, right, that if I look at E squared equals MC squared plus PC squared, if those particles are moving very, very fast, their total energy can be large compared to their rest energy. Right? They can have so much kinetic energy, it's very large compared to their rest energy. And in that case, why, you could throw that term away and come up with approximately E is just PC. Does that remind you of a relation between energy and momentum for anything you know? Why, that's the energy-momentum relation for photons, right? For photons, right? Well, pressure is related to momentum. Energy density is related to the energies of the particles, right? So in other words, for an ultra-relativistic ideal gas, they start having essentially the same relation between energy and momentum that photons do. So how do you think their energy density and pressure are related when the gas is ultra-relativistic?
They're the same?
Yeah, for an ultra-relativistic gas, you get that the pressure is 1/3 of the energy density as well, in that limit. So, in other words, what this is ultimately coming down to is whether the particles are non-relativistic versus relativistic. The photons are all the way relativistic, but any particles, if you make them ultra-relativistic, this becomes very nearly the relation. And the more relativistic they are, the closer this comes to being exact. So, kind of a fun connection. Okay.
Who is precocious now?
Did you say it?
Yeah, I did.
You're precocious. Yes, there you go.
It's fixed.
There you go. You're precocious. Yes. Yeah, there you go. Were the rest of you precocious too, or you just?
They were, but they're humbler than I am.
Well, okay, right. Yes. Okay, very good. Yes. You're arrogant. No. No.
I get it from you.
Whoa. Whoa.
Just kidding.
I am so not going to show this video to my
Would you
Yes.
agree? I'm sorry.
This is because she likes to cry. It's funny. Never mind. Okay, so that's funny. So anyway, she likes to cry. Actually, I do have to show it to her because she'll be very amused.
Does she use your emotions?
No, because she thinks I have a big head. And so, we tease each other, right? She says I have a big head. And I point out that no, my humility is just one of my many outstanding qualities. So, all right, so continuing. I actually don't have a big head, seriously, but she likes to have a big head. So, just because I like to, be a ham in front of crowds, right? But that's not having a big head, is it?
No.
No, certainly not. No, not at all. Okay. One more thing with this. If the radiation field is not isotropic, we'll still have the p-rads given by that interval. We still have that p-rad is 1 over c times that integral, pi lambda cosine squared theta d omega. But when that happens, we just physically see that if p-rad isn't isotropic, then the force on a surface will be larger in directions where the specific intensity is greater, and smaller perpendicular, where the surface is perpendicular to directions where the specific intensity is smaller. In other words, with pressure, with an isotropic field, the force on a surface in magnitude doesn't depend on the orientation of the surface. The direction depends on the orientation, but the force itself is the same no matter how I orient the surface. But for a non-isotropic radiation field, there would be different forces on the surface for different orientations. And then we say that we would not be dealing with an isotropic pressure, but with an anisotropic tensor, like a stress tensor for the radiation field. So I'll just put that down. But now, the force on the surface depends on the magnitude of the force. Because the force always depends on the orientation in terms of the direction, magnetic force. The magnitude of the force on the surface depends on its orientation. And the fancy way to say that is the stress tensor is not diagonal. And we don't need to dwell on this, but to just, kind of like give you a little flavor of the idea. In general, the force on the surface would be, you would take a matrix and multiply it by the components of the normal vector, and that matrix would be called a tensor. And if it's a pressure, then that matrix has the form that is just the pressure along all three components of the diagonal and 0 everywhere else. So in other words, you would say like f sub x, f sub y, f sub z, multiply that matrix, 0, the giant zeros there just mean this is a 3 by 3 matrix, it would be 0, 0, 0, 0, 0, 0. Those are just, right, that's just a quick notation for a matrix where there's zeros everywhere except for the components where you put not zeros there. And so if you do this, right, if I did the matrix multiplication, it would be p times nx plus 0 plus 0. So this component would be p times whatever nx is. And this would be p 0 times nx plus p times ny plus 0 times nz. So it would be p times ny. And this would be p times nz. So in other words, it would be just the number p times nx, ny, and z. Or in other words, the force on the surface, force per unit area, I should say, because I should really multiply by the area here. So the force per unit area would be the pressure times the unit normal vector. The force is in the same direction as the normal to the surface, and that's what we've been talking about. You hold the surface, whatever orientation, the pressure pushes along the direction of the outward normal of the surface in that case. But, and in a gas, that's almost always the case. That's typically the case because there's no reason for the gas particles to flow more strongly in some directions than others. But in a solid, or in a non-isotropic radiation field, because that's not too hard to set up, well then you get a stress tensor, where in other words, it's not just that you have the same number along the three components of the diagonal. In general, you would have a whole matrix here, and then the force doesn't point in the same direction as the normal does in general. In a solid, where you have a stress tensor, the force doesn't necessarily point in the direction of the normal, because in a solid you can have pushes and pulls that are along the direction of along the plane of the surface and not just perpendicular to it. So things get more complicated. This is not a material science course, and so we'll just stop there. Just throwing that in there for kicks. Okay. What questions do you have? Okay. We have 6 precious minutes here, so I'll start the next topic, which is measures of temperature. There's only one situation in which temperature is truly well defined, and that is perfect thermodynamic equilibrium. In general, there is no such thing. There's nothing in perfect thermodynamic equilibrium. There's just approximations to it. It's a good thing. If the universe were in perfect thermodynamic equilibrium, would we be having this conversation? No. A perfect thermodynamic equilibrium universe would be homogeneous and isotropic. And you represent a non-homogeneity in the universe, right? That the universe is not exactly the same everywhere within it. Boy, perfect thermodynamic equilibrium would suck. But in general, there's just no place that's in perfect thermodynamic equilibrium. So really, there's no such thing ever of perfectly well-defined temperature. And so we have to talk about different measures of temperature. And the idea would be that in thermodynamic equilibrium, all of these measures of temperature would give the same number. But in reality, there's never perfect thermodynamic equilibrium. And the closer you are to thermodynamic equilibrium in some sense, the closer these numbers will be to one another. But you can definitely have a situation if you're well out of equilibrium where different measures of temperature can give very different results. So let's make a list of some measures of temperature. We probably won't be able to complete the whole list today, but we can at least get it started and be all excited for continuing it later why there's effective temperature. We've met this one before. Effective temperature. Right, that's our TEF. How do we define that? We said that the flux is sigma TEF to the fourth by definition, and for a perfect black body, F is sigma T to the fourth. But even if the radiation isn't perfectly described by the Planck function, we can still say the total flux from the surface is sigma TEF to the fourth. We can define TEF to the fourth to be whatever the total flux is divided by sigma and just call that the effective temperature. So TEF is equal to TEF to the fourth by definition is F over sigma from our surface. That's from the Stefan-Boltzmann law. And then we can talk about the excitation temperature, which is always high in this class because you're excited to learn. Wow, that was really good. The excitation temperature. And that comes from looking at the populations of different energy levels in the atoms. And what equation was telling us the populations of different energy levels in the atoms? Why, that was the equation. What did that one be?
Boltzmann.
Yeah, the Boltzmann equation. Exactly, yes. How very precocious of you. Yes. From the Boltzmann equation. Now, since you're never in perfect thermodynamic equilibrium, the actual distribution won't look exactly like the Boltzmann equation. That's a symptom of not being in perfect thermodynamic equilibrium. But the closer you are, the closer the Boltzmann equation is to getting it right for your situation. And then there's the ionization temperature. Ionization temperature. From the, Anushka, you'd be very embarrassed if you weren't able to tell me what this one is from.
But I know what it is.
But you know what it is. It is
Saha.
the Saha equation. Yes, indeed. So you're not embarrassed. You're precocious too. We're all precocious. It's from this. Woo! Yes, yes. The Saha equation. Yes. So I forget. Is it?
Magna.
Yeah, Magna. Is it? How's the accenting go? Is it Saha or is it Saha? Is it
Oh, it's right as you see it.
Saha? Saha. Okay. Aha. It's Saha. Okay. Yes. All right. And then there's the kinetic temperature. Why, that would deal with how kinetic energies of the particles are distributed, or maybe even how their velocities are distributed. And we talked about some sort of distribution of speeds. Who's that named after? Maxwell-Boltzmann. That's right, from the Maxwell-Boltzmann equation. The Maxwell-Boltzmann equation is based on that. And then finally, we'll end with color temperature. Color temperature from, and you could say Wien's law, and I would give you credit, but we're going to say from the, who's the person who came up with the very idea, well, not the idea, but showed how, what do we call V lambda? That's whose function? Planck's function, right? The Planck function. I would make you walk the plank if you didn't know that. From the Planck function. Right. So the idea then would be, for example, to get the color temperature. you could look at the actual plot of intensity versus wavelength and find for what value of the temperature would the Planck function for that temperature give the best fit to the actual distribution, for example. And then you can say that's the color temperature. You can also do things like Dean's law. You can say, well, where's the peak wavelength as long as it's reasonably two? If you're far from equilibrium, like, you know, if your spectrum is a bunch of spectral lines and nothing else, it's an emission line spectrum, there's no point in trying to define the color temperature. It's just nowhere close to being a Planck spectrum in that case. But if you're reasonably close, you can do it. And so the big picture here is, in pure perfect thermodynamic equilibrium, every definition of temperature agrees. And so that's what, you know, in the real world, they never perfectly agree. The closer they all come to agreeing with one another, the more reasonable it is to say that I'm close to thermodynamic equilibrium. And that's where we'll stop for now. Okay, so we'll take it out. Yeah, yeah. No, I meant it. It's the excitation temperature. That's right. It's good. Okay. All right.
I think you're talking about the Volcker equation while you're in.
Oh, yeah. That's true. That's good. I like that. And preserve for posterity. I'm not going to edit this. This is good. Gotcha.
It's the new rule, maybe.
That's right, yes. The excitation. I like it. Yeah. It does. Thank you for pointing that out. Yes. Because I would have been blissfully ignorant of it had you not pointed that out.